Okay, we're going to try and get this to work. This is like my 7th video. It just won't save on my computer, stupid computers. Enough about that. Okay, bonding metallic and ionic with Lewis structures. That was my subject. Here's your joke. Very funny, I know. Key terms are in here: ionic bonding, metallic bonding, lattice structure, Lewis dot structure, delocalized electrons, and octet rule. So we're going to do an FRQ first. So suppose that a stable element with atomic number 119, symbol Q, has been discovered. So write the ground state electron configuration for Q, showing only valence shell electrons. Okay, so we're going to look at a periodic table. So looking at this periodic table, we have 114 over here, so 115, 116, 117, 118, 119 is over here in this first row, first group. So technically it would be like right under francium. So we'd assume that it would be 1, 2, 3, 4, 5, 6, 7, 8. It would be 8s1. Boom. Okay, B. Would Q be a metal or a non-metal? Explain in terms of electron configuration. So again, looking at the periodic table, we see that it's under the first group, and all of these have one valence electron. They have one valence electron, so we'd assume that this would be a metal, since these are all alkali metals, or just, it can be an alkali metal or just a metal. You can say either. I think they accept both, but that's pretty much what it is. So again, metal. And then, what would most likely be the charge of the Q ion in stable ionic compounds? Okay, I think I already gave that away. So this is the group 1, and they're going to have a +1 charge. Alright, so you can go through and check those. It's here if you ever want it. So here's another joke. That's what my report card looks like. Just kidding. I'm very smart. Okay, the real types of bonding. Alright, so looking at ionic bonding, which is like diagram C, we can see that the Na is donating a valence electron to the chlorine, which is making them both ions, and chlorine and chlorine and sodium are both reaching octet rule, which is where they each have 8 valence electrons, just in different forms. Okay, ionic bond sodium chloride. Okay, so again, sodium chloride, which is going to be my main example in all of this. So we see that Na is the smaller one because it's got less valence electrons, and it's located earlier on in the periodic table, and then chlorine's the bigger one because more valence electrons, etc. So they're going to have like a little bit of a repulsion because of the electrons they have, but this is going to be a more inner, Na is going to be an inner electron, while chlorine's going to be an outer electron. Alrighty, metallic bonding. Alright, so metallic bonding, we always hear about the C delocalized electron, so here's their technical delocalized electron, which is usually the mobile electron. So in the sea of delocalized electrons, there's like the metal, and the electrons are going through like little holes, like helping like a circuit go through the metal. Usually that's what we talked about. Again, this is sodium, another example of the same, but it really just shows you how like metallic bonding is set up and how these like little electrons move. Okay, Lewis dot structures. So again, sodium chloride. So we see our 1 valence electron on the sodium and 7 valence electrons of chlorine. They're going to come together. Sodium is going to lose its 1 valence electron to chlorine, making it an ion, and chlorine as well, because it reaches octet. So that's always exciting. And then lattice structures. Okay, so here is lattice structures. We have the outer electrons, which is the chlorine ions, and the inner electrons, which are the sodium ions. The sodium ions kind of tuck away in between the chlorine ions, and that's how lattice structures form. So that's why salt is kind of its shape and fun things like that. I can't even speak. Okay, so don't forget that metallic will also have lattice structures, but sometimes they're shaped a little bit differently depending on whether they're an alloy or just like a pure metal. Alright, we're talking about solubility versus insolubility. Okay, so it says a salt is insoluble if the concentration of an aqueous solution is less than 0.001 molar at room temperature. So you can really think about KSP for this. I'm not going to go into detail about KSP, but solubility product, so really you can figure out how soluble a certain salt is. Usually salts are soluble, but sometimes they don't like water or other elements because of their polar abilities and stuff. So things to be aware of for insoluble salts: anything that's a sulfide, an oxide, a hydroxide, chromate, or a phosphate. So there are exceptions, and you can always come back and look at the exceptions. So don't forget about the exceptions. I'm sure you can you can memorize this. It's pretty easy. There's only 5 of them. And then our last joke. Graduated cylinder versus dropout cylinder. Ha ha ha. Okay, well, that's about it. And that's pretty much ionic and metallic bonding with Lewis structures. Thank you!